some practice calculating an equilibrium constant from a set of data. So here we are, we're back again at this water-gas shift reaction. And you notice we have a whole bunch of data. We have initial concentrations and we have equilibrium concentrations. So in these initial concentrations, what you have to imagine is if a scientist were conducting this experiment, for example, in experiment one, they might have zero point zero 0.02 molar of CO and zero point zero 0.02 molar of H2O. And of course, they don't have any H2 or CO2 to begin with. And then, of course, they mix that H2O and CO, let it react. And then now the equilibrium concentrations you can see become the following: 0.0036 molar of both CO and H2O, which makes good sense that they both end up at the same concentration because they have the same stoichiometry, right? But now you notice that H2 and CO2 do not become the same concentration as CO and H2O. Rather, it's some amount less than what they started out as. Okay, so now the H2 and the CO2 become 0.0164 and 0.0164. So how do we calculate an equilibrium concentration from this? All right. Well, we'll write the equilibrium expression for this reaction once again: products over reactants. So that's H2 times CO2, all divided by H2O times CO. And now what we're going to do is just plug that data in. Okay. So for example, if we do experiment number one, we're not going to use the initial concentrations. We're going to use the equilibrium concentrations. Okay. So now my Kc will equal, let's see, so it's H2. So that's 0.0164 times 0.0164. And then now that's all divided by 0.0036, all times 0.0036. Okay. And so what does this all equal? Well, let's do it. You can see I've got my online calculator here. So we'll say 0.0164, and I'll just say squared because we know that it's being squared, right? And then now I'll divide that by 0.0036, also squared. And then now on the scientific calculator, I say equals. And there we go. So we have, for this calculation, it'll be 2 sig figs. So 20.7 with 2 sig figs becomes 21. And so now what about the units? Okay, so equilibrium constants are unitless. Okay, and as you can see from this particular set of data, right, the molar and the molar would all cancel. But even in an equilibrium constant expression, when those molarity units don't cancel, we still just call an equilibrium expression unitless. Okay. So now, well, what about experiment 2? So, well, you can see in experiment 2, this is rather interesting. Now, in this experiment, they started with the same amount of reactants, but this time it was H2 and CO2 that they started with, and 0 CO and H2O. Okay. And as you can see, the equilibrium concentrations end up being the same. So then we know that we'll get the exact same equilibrium constant for experiment 1 and 2. And that's why it's an equilibrium constant, because no matter what the starting concentrations are, the equilibrium concentrations will end up giving us the same value for the equilibrium constant. So to prove that, let's do this number 3. Let's take a look at that one. Okay, so Kc for number 3. So we want to use the equilibrium concentrations. And notice here that in this experiment, they started out with amounts of everything: 0.01 molar CO, 0.02 molar H2O, 0.02 molar H2, and 0.01 molar CO2. And then now we end up with these equilibrium concentrations. So let's plug those in. So that's the H2 concentration. So that's 0.280 times the CO2 concentration, that's 0.0180, and now all divided by the CO concentration, 0.0020, and times the H2O concentration, 0.0120. Okay, so now let's see here. So we can do this by saying 0.0280 times 0.0180 equals, and now because this is all being divided and multiplied, I can actually just say now this divided by 0.0020 equals, and then now I could say divided again by 0.0120 equals, and look at that. We actually get right at on the money 21 for the equilibrium constant, okay? And just to prove that this works, right, for number 4, you can see once again a whole different set of concentrations. And if we were to go and calculate all of this stuff, so I'm just going to put in all of these values here and calculate them away. Okay, so let's do that. So we'll clear that answer out. So 0.0350. I know I don't have to put the extra 0 in there, but I'm doing it just to be complete. 0.0450 equals. And then now we'll say divided by 0.0150 equals. And then once again, divided by 0.005 equals. And we got 21. Okay, so you can see here with the equilibrium constant, it is a constant. No matter what the starting concentrations are, the equilibrium concentrations will always end up being the same for a given reaction. Now, if this were a different reaction, of course, we would get a different equilibrium constant. Okay, and then the last thing I'll say about this reaction, we note that these are all equal, the equilibrium constant is greater than 1, okay? So for this water-gas shift reaction, we would say the equilibrium position is on the right, okay? So if we have any amount of H2O and CO, as you can see right here, it doesn't matter how much H2O and CO we start with. Once we let them react, they're going to produce more H2 and CO2 than is remaining in H2O and CO, right? You can see that the reaction doesn't go to completion. There's CO and H2O remaining, right? However, because the equilibrium constant is greater than 1, the equilibrium position lies on the right.